everybody? So I was discussing with your classmate that this was our class. So instead of having it in class, maybe it would be better if I just record a video. Then you guys will watch it, then you will assign them. There will be a lab, like it's a lab. So you are going to watch the video then based on it to complete the lab exercise, class exercise. So I was discussing with your classmates, so you can give me just discuss among yourself. Then, or you already decided. Yes. So what is the what? Have you decided? Okay. So please just discuss among yourselves, then let me know your decision. So we are going to continue from where we stopped yesterday. So the data set we're working with, it was a used car data set. So it had different models of cars in different Excel documents or different Excel sheets. So and it had different colors. So these are the different colors of the car. So our task is to, based on several features, our task was to predict the price of the car. So that was what we did. So throughout yesterday, when we had the class, so we went through the process throughout yesterday when we had the class, so we went through this process. So we tried to explain each of these process in detail. So this is the name of the folder, car prices. So this is just to load the data from the folder. Then we talked about this function. This function is to filter the data. So when we looked at the folder, we saw that there were some CSV files that there were no car manufacturers. They were just, we don't know where they came from. So this function here, filter for data, was to clean the data, to remove the unwanted CSV files. Then here we opened the file as a read file, and here we started to read the CSV file. So since it's a CSV file, CSV stands for comma what? Values. So it means that the values are delimited with a comma. So we are just trying to read the CSV files using the format, that's comma separated value. So we know that the delimiter is comma. Then we skip the first line because the first line is just the header. Then this function we said was to get the manufacturer, because it turns out that the file name of each of those CSV files, they were car manufacturers. So we wanted to get the file name and include it as a feature. So we talked about this function. Then this function is to do pre-processing. So the pre-processing we did was the pre-processing on the categorical attributes. So what we did was that we did drop-down encoding. So when we looked at the data set, we discovered that some of them were having alphabets So we did drop down in case of in place of those alphabets. We'll just replace it with an index, maybe 0, 1, or 2. Then after that, we try to split the data set into train, validation, and test. Then we shuffle it so that there is variety in the training set. So that's where we stopped in the last class. So we are going to continue from where we stopped. So we did all of this process. We loaded the data, we cleaned it, we pre-processed it, we built the data set or data pipe, then we built the data loader. So we are here in the data loader section. So the data loader section is just simply how you want the data to how many chunks of data do you want to feed into the model for each iteration. So the batch size, the chunk of data is specified here is 128 by 128 by 128. So can somebody remind me, how did I explain train, validation, and test sets? Can somebody remind me what's their use, what's their function? Anybody? What's a training set? What does it involve? The validation set, what does it involve? Then the test set, what does it involve? The model sees when it's developing the model. So that's the training set. So the validation set, the model too is exposed to the validation set, but it's just to do minor adjustments to the parameters and hyperparameters of the AI model. Just look at it once in a while to just try to adjust itself and make the model even better. Then the test set is like the AI model has always seen the test set only once. So, and it's when it wants to make a prediction and it wants to get the accuracy. So in other words, the training set, the AI model sees the training set like as much as it wants to see it. For the validation set, the AI model sees it, but just not that much. It looks at the validation set, but it doesn't train much on it. It just uses it to make adjustments. Then the test set is the AI model just sees it once, and the once it sees it is when it actually wants to make a prediction. Then so that's why we stopped yesterday. So we're going to continue. Yesterday we talked about the continuous attributes and the categorical attributes. So we look at the continuous attributes. So the continuous attributes, let me go up. The continuous attributes of the data sets are the year, the mileage, the road tax, the MPG, and engine size. Then the categorical attributes are the model, transmission, actual. So the next step is to just do exactly what we did last week. So what did we do last week? We got the continuous variable and the categorical attributes. Then for the categorical attributes, we did ordinal encoding, where each of the features will represent it by an embedding, and we specified the number of columns of the embedding we want to use. So we've done that last week. So it's the same structure. Then for the continuous attribute, what form of preprocessing do we do on the continuous attribute? Yes, standardization. So we standardized it. So in this case, what we are going to do is that we will do ordinal encoding on the categorical attribute. Then we'll do standardization. So what this layer is all about is the standardization. It's just basically the standardization we're talking about. So after that, you combine the both of them together as features. So these features will act as the inputs. Then you can specify as many hidden layers as you want. Then of course the activation layer to add non-linearity to it. Then there is something we are introducing. For this particular model that we did not introduce last week. After the activation, we did another standardization. So first of all, we did standardization on the continuous attributes, but the result of this, before feeding it to the output layer, we introduced another layer called the batch num layer. And what the batch num layer is simply doing is standardizing the output from the hidden layer before it eventually gets to the output layer, and of course it makes the prediction. So I will just describe the code. So if you are able to do last week's exercise, you're able to really understand the code. So what we have here is just the ordinal encoding that we are doing on the categorical attributes. Then after that, what are we doing here? So this is the batch num ID. So, and I said the batch num ID is the standardization. So can somebody tell me what this line is doing? So n_cont are the continuous attributes. So can somebody explain what this line is doing for me? So what this line is doing, somebody? This line that I highlighted is just this form, it's just here. So it's just at this point where you have the continuous attribute. So what is that line doing? What's that line doing? Yes, it's standardizing what? It's standardizing the continuous attribute. So look at it. You are standardizing the continuous attribute. So that's what that line is doing. So after that, this is the hidden layer. So what this line does is to combine the features of the continuous attributes and the features of the categorical attributes. Then it adds the number of hidden layer. Then after, so that's what this particular line is doing. So can somebody tell me the result? What would be the result of this operation? So the result of this is the categorical attributes, the number of features of the categorical attributes. While this are the number of features of the continuous attribute. So can somebody try to tell me what is going to be the result of that arithmetic? What do you say? How about the features? How many inputs do we have? How many neurons do we have in the input layer? How many neurons do we have? No, it's not 10. How many neurons do we have in the how many neurons do we have in the input layer? How many? Can somebody tell me? How many neurons do we have in the input layer? That's the question. Who is saying something? The total number of what? Do the calculation. What's the calculation? Seven. How many neurons do we have in the hidden layer? In the input layer, sorry. How many neurons do we have in the input layer? That's the question. So nobody in this class knows it. Nobody in this class knows it. It's a calculation. You have to do a calculation. Okay, so let's do the maths. So my question was, how many number of neurons do we have in the input layer? So these are the attributes. These are the categorical attributes, and these are the continuous attributes. So for the continuous attributes is 1, 2, 3, 4, 5. So that's 5. But for the categorical attributes is 1, 2, 3, 4. So that's 4. But it turns out that for the categorical attributes, we did an embedding called the ordinal encoder. So for the ordinal encoder, you need to specify the number of dimensions that you want for that embedding. And in this case, nobody asked me what is the number of dimensions for that ordinal encoder. Because in the last class, remember I told you that you should change the number of dimensions to a particular number. So it turns out that for this code, if to say somebody understood the question, the next thing was for you to ask me that what is the number of dimension for the ordinal encoder. So if somebody has asked me, I will know that you understand how to solve it, but since nobody asked me, so I know that you don't even understand how to solve it. So for this particular code, the number of dimensions set for the ordinal encoder is what? 5. So what this means is that this 4 is for the categorical one. So you multiply 4 by 5 because the number of dimension is 5. So what this one is saying is that instead of one of these features, split it into an array that has 5 different values. So the number of neurons is 4 times 5, which is 20 plus 5, which is 25. So the number of neurons in the input layer is 25. So here is, so what this means that here, the result of this calculation here, so here is 25 and here is 100. Then after that, we did, so this is the hidden layer here. Then we applied a batch normalization, which is the standardization on the hidden layer. Remember that the hidden layer has 100 neurons. So that's why this 100 neurons is there. So we applied another normalization at this point on the hidden layer. So let me show you the diagram again. So after this hidden layer, of course there's an activation, then we applied another normalization on it, then before you go to the output layer. So after applying the normalization, then you get to the output layer. So this is the structure of the neural network. Then of course the activation we applied is ReLU. So we've already developed we've built the AI model. So here is just to list the different, so we have 5 continuous attributes and we have 4 categorical attributes. So this is 1, 2, 3, 4. So somebody can be asking, where did I get this? Where did these numbers come from? So the numbers came from, let me open the data set for you. So let me open the data set for you. So the numbers you see here. So for those of you that were around yesterday, we were trying to do this encoding yesterday. So it turns out that, and you know that we added all of the CSV files. So for this one, the different values, it turns out that the different values started from 0, then it ended at 194. So for this second one, it turns out that there are 4 different values starting from 0 to 1. So this second one represents, let's go back to the data set. So this second one represents the second categorical attribute, which is transmission. Then the third array represents the foil type. Then the last array represents the manufacturer. That's the manufacturer of the car. So that's how we got all of these values. So we've built the AI model. Then now is to define the loss function. The loss function is defined as a mean square error. The next step is the learning rate. So this is the learning rate. So the optimizer uses the learning rate to actually update the weight. So what does this mean? 3 exponential minus 3. So in numbers, what's this number? What's this number? So this number is simply means 3 times 10 raised to the power minus 3. And that's 0.003. So 0.3. So this is the learning rate. It's 4. Okay, so that's 0.003. 1, 2, 3. Okay, so this means that this is the learning rate, and we are using the Adams optimizer. Then after this is to train the AI model. So this is the code for the training. After that, you do validation. So you have been able to train it 100%. So you can specify the number of epoch. So the number of epoch was specified as 20. So 20 simply means the number of iterations before you stop training the model. So you can change the number of iterations. Then we are plotting the loss function of the training and validation set. Then after that, we are now making a prediction. So this is the actual value of the price, and this is the predicted value of the price. Remember that the AI model is to predict the car price. So based on the model, the AI problem is to predict the car price. So based on the model, the model was able to do this prediction on the test set. So it was able to do this prediction on the test set. So this is the actual values and this is the predicted value. So we can compare and see the results. Then the final thing I want to emphasize before we close and I give you the assignments to do is the metric. So can somebody, before I talk about the metric, can somebody that knows about machine learning previously, can you tell me the different metrics, performance metrics we use in machine learning? Yes. Accuracy. Recall. Yes. True positive. Yes. False positive. Yes. How to. Okay. So it turns out that all of the metrics you've told me, you just said, apart from how to, she said, those ones are for classification problems. And are we dealing with a classification problem or a regression problem? Regression. So it turns out that all of these things you've listed, we cannot use it. So for regression problem, the metric we use, the performance metric we use, let me just try to give you a list. So these are the different performance metrics we use. So you can get the maximum error, the explained variance, the mean absolute error, mean squared error, root mean squared error, all of these. Then R squared. So R squared simply means the coefficient of determination. So R squared is a metric that is the most common metric we use for regression problem. So let me just write down the formula for the R squared, because in this case we are just calling a Python function here to just get the R score for us. But let me write the equation for the R squared. So R squared is equal to 1 minus summation minus h of omega x squared divided by summation y minus y bar squared. So this is the formula for the R squared. And I said it's a performance metric for regression problem. It's the most common performance metrics for regression problem. So R squared stands for coefficient of determination. So let me just simply describe it. So for instance, if you have your x here, which is your input, then you have your y here, then your prediction is given by W0 plus W1x. So this is your h of omega x, and it's the same thing as the prediction. So h of omega x is the prediction. So after that, what you just need to do is subtract this y minus this column h of omega x. So after doing that, then you square it. After subtracting, you square, then you sum it together. So it will give you this value. Then for this is the mean of y. So look at y here. You get the mean of y. Then you have another column, y minus y bar, which is the y minus the mean of y. So you get the values. For each of the values of y, you subtract from the mean. Then after that, you get the summation. So the summation, and you square it. Before summing it, you have to square it. So after squaring it, you get the summation. So you put this summation here, you put this summation here, then you subtract, you do this subtraction. So that's the formula for R squared. But we can simply use a Python. We import from scikit-learn library. Then if you import this, you would import the R squared also score. Then you just put in the true value, the actual value of y, then the predicted value of y. Then it's going to return the R squared value. So the R squared value should be as close as possible to 1. So the R squared just is an indication of the accuracy. So instead of calling it accuracy, accuracy is basically for classification problem. But when we get to regression, we don't talk about accuracy, we don't talk about F1 score, we don't talk about all of those things you were mentioning. It is R squared score we talk about. And I have told you the formula. So that's the metric we are going to use. And I said we want it to be as close as possible to 1. So once it is very close to 1, then we know that we are really very good. So that's that's what we are going to do for today's class. Then for the class exercise, because this is a lab, the exercise is to print all the other evaluation metrics. So I've listed all the other evaluation metrics: the mean square error, the mean absolute error. So, and here I'm only printing the R square score. So the first instruction is to print out the other evaluation metrics. So like I said, is the R squared score that is the most important, but I just want you to print it out, so just for visualization's sake. Then the next instruction is to experiment to determine what model gives the best performance. So what I mean by experimentation is that you change certain things in the model. Like you can change the embedding dimension. You can decide to, one of the things I was saying yesterday was that the year column, it was included as a continuous attribute, this year column. So another thing you can do is to change from the year column, which is a continuous attribute, you try to put it in the categorical attribute. Another thing you can do to experiment is to change the structure of the model. So when I was asking you about the number of neurons in the input layer, so we calculated it as 25. So the way you can change it is either you change the embedding to make the number of neurons in the input layer either more or less. You can add more hidden layers. So you can add more hidden layers. You can change because after the hidden layers we did normalization. So you can decide, maybe I don't want to do normalization. You remove this batch standardization layer. So you just change the parameters. You can change the learning rate. So the learning rate here was set to 0.03. So you can decide to change the learning rate to another value. Maybe you will get a better score. You can change the optimizer, experiment with different, like I said, experiments. So you would use different values, you can change the loss function too. You experiment. You can change the number of iterations. Probably we are using 20 iterations. So why are we stopping at 20? Why can't we go 100? So you can change the number of epoch. So these are the things you can change. Then what you are looking for is the R-square value. So in the last assignment or in the last exercise, I was like, you should just report your observations. But now, what you are actually observing now is the R-squared value. So you do some of these changes, you run it, you would observe the R-squared value. Is it worse or is it better? You change again. So experiment, that's the key word. So you will change something, find the R-squared value, change another thing. So you want this R-squared value to be better than what we have based on our current model. So our R-squared value is currently at 0.935, but we want it better. So that's the exercise for this lab. So is this something you can do? Okay. Yeah, I will put it on module. I'll put it on module. What is it? When should I do it? Next week when? Okay. Alright. So you can just let me know. Because this class, I don't know. It seems it's not convenient. So let me know your plan of how we are going to handle this 1 hour class. Yeah. I'll put some photos. Then also upload the collab link. Also, it's the same thing we did last week. So you will upload the collab link and you would also do a video. So I was watching some of the videos. Some of you didn't follow all the instructions. So especially the number of, I told you to add more hidden layers. Most people did not add more hidden layers. They just did the others. They didn't add more hidden layers. So please try to follow all the instructions. So this instruction is experiment. So you will change something, then you calculate the R-squared, how to score. You change another thing. So until you arrive at the best model. And the indicator of the best model is a how to score that is higher than the one of this model I presented. Yes. Okay. So the highest is 1. Yes. The highest is 1. So the least is, I don't know, 0. The least is 0.